do natural log of 4 on your calculator, divide by 5.9. So not quite 6. Wait a minute, hold on, I got something else. $5.999, is that what y'all again? Yeah, so it's almost, it looks linear, doesn't it? But it's because we're not, this growth rate is 0.23. Maybe, I don't have the computer up. It would be cool to look at that graph, but I'm just going to go with 5.99 as t. What do you think? I'm not going to go through this work in detail, but how long do you think it would take to double again? Oh, hours. Sorry, forgot hours. How about to double again? So it doubled it initially, it went to 2, right? Double that, you get to 4. Double that, you get to 8, right? Not 6. So has anyone noticed a pattern in this? Like this right here, if I wanted to know how long it took to double a third time, that means it would be 8 times the initial amount. Wouldn't this just turn out to be natural log 8 equals 0.23105? Do y'all notice that this number right here is how many times bigger it is?
It's like 8.9.
You did this one? So 8.9?
8.99.
99? Okay, equals t.
Yeah.
What about to double again? It would be natural log 16 equals 0.23105 t. Do that one for me. What do you get?
11.9.
11.99 t. Go one more. Let's double again. 32, right? What do you get there?
14.9.
14.9?
So it's kind of like
It looks, yeah, this looks almost linear, but it's not. No, is it what?
Is it wrong?
It's not wrong. It looks linear in the beginning. Hold on, let me, I'm gonna graph it real quick. I wanna see when it starts to really take off. I know y'all won't be able to see this, but, okay, so. I want to show this to you all so that you can see it. Let's see. Okay, so take a look at this graph. I don't know if y'all can see this, but do y'all see that? I've graphed part of this exponential function. Kind of looks linear, doesn't it? It looks almost like a line. I mean, there's a little curve to it, but you could almost say that that's linear, yes? Now, I'm going to zoom out a little bit, a bit, all right? I'm going to zoom out a lot. Okay? So, see, what's happening is that there is exponential growth, but it's not really taking off till later. See that? So, in the beginning, it looks almost linear. But if you zoom out far enough, it starts to eventually like take off and not look linear anymore. So that's good. All right, we good? First 2 examples? Yes? All right. Last problem. And this is my favorite out of all of these problems we've done. This is my favorite because it's the most applicable one. So how many of you all have heard of something called a half-life? Right? Not the video game, right? Yes? Half-life? So what is can you explain, somebody explain what half-life is? What the half-life of something is? How long it takes for something to decay to something else. Okay, yes, anyone want to elaborate on that? You look like you want to elaborate. No? So the half-life of something is basically, look, in the universe, okay, certain things start to decay and go away, right? I think of it like a campfire. Have you ever had a big bonfire? It's real hot, and then you put all the wood in there and you let it burn. It's real hot in the beginning, and then you come back 3 hours later, it's still hot, right? And then 10 hours later, it's still hot. You come back the next day, it looks like it's out, but you poke in there, it's still hot in there, right? What's happening is the heat is kind of going away. It's not exactly the same, but it's the idea that it goes away, but it kind of lingers, right? A half-life is similar. You have some material, whether it be carbon or some radioactive material, whatever it is. Let's just say we start and here's how much we have, right? And I'm going to say the amount we have in the beginning is A naught. Depending on what the substance is, if it's decaying, right, then what will happen is it will take some amount of time for it to now be, well, let me draw the picture a little different, about half of what it was before, okay? So it's like the fire was real hot, and then it takes a certain amount of time for it to be half as hot as it was before. And then that time right there, okay, that time, if you take that time, let's just say, just for the sake of demonstration, let's say that this was 2 hours. It took 2 hours for it to decay halfway. Then 2 hours later, okay, so plus 2 hours, now you're going to have, half of that will decay. So how much of it do I have? Half of a half, right, is a fourth. So I have 1/4 of what I started with. And then 2 hours later, half of that, 1/8 of that, right? And then 2 hours later, what, 1/16. 2 hours later, 1/32. 2 hours later, 1/64. So what's happening is it's decaying away, right? Now, does it technically ever go completely away? No, I mean, it gets infinitesimally small to the point where it's negligible, right? But theoretically, it never completely goes away. The amount of time it takes for half of it to decay is called the half-life. So the half-life of this particular example is 2 hours. Certain objects take certain amount of time for the half-life. It could be seconds, it could be hours, it could be days, it could be years, it could be thousands of years. So y'all have your phones, right? You can look this up. Let's take something. We'll do this example here in a second, but let's just do something more applicable. Look up the half-life of ibuprofen. Y'all take ibuprofen, right? You get muscle aches, headaches, or just for fun, right? I don't know, right? Ibuprofen,
Yeah, I don't really just take it for fun.
You don't take it for fun? Okay.
No.
You do?
Yeah.
Okay, just kind of with breakfast.
Does it work?
So did you look it up?
It's not working.
Not loading? Anyone else? It's not coming up? No internet? No internet, huh? What the hell? Can't get it in this building? 1.9 to 2.2 hours. Let's go with 2.2 hours. Okay? Hey, it's almost this example. But let's go, we'll go with 2.2. Let's make it a decimal. All right? So the half-life of ibuprofen is 2.2 hours. So the idea is this. If you take, I don't know, do you all know what like decent dosage for ibuprofen is? Each of those, most tablets are 200 milligrams. So depending on what you normally take, the most I think you should ever take, I think, is 800 at one time. That's like exceptional. 600 is pretty high. 400 is okay, like for an adult. Let's say though you took some ibuprofen, right? What this is saying is that 2.2 hours later, about half of that ibuprofen is basically decayed away, and it is no longer having an impact on your bloodstream at all. Like it's not. Make sense? So here's the question. That's it. That's all this is the only information we're given. All right. So from this, we're going to answer some questions, and so I'm kind of skipping this right now. Okay. So for this problem, here's the first question. I want us to find a function which models this uninhibited decay, because it's going away, right? All right, well, it's going to have to be this generic model, right? It's that generic model because I'm saying it's uninhibited decay. So let's see what we know. Shit, do we know anything?
A of t is 1/2.
A of t. So we know that, okay, yes. Let's write it down first. This is what we know to start, right? This is all we know to start. Did I give you an initial amount?
No.
Did I give you a decay rate?
No.
Not directly. I did not give you a decay rate. And I didn't give you a t, right? Not right away. But this information right here should be enough for us to figure out the actual function, all right? But at least the decay rate. So what does it mean that the half-life is 2.2 hours? It means when I plug in 2.2 for what? For t, I should have how much there? Half of what I started with, right? Half of what I started with. So what I can do is I can say this side right here is half of what I started with. If this is what I started with, half of that, right, happens when t is 2.2. You see? And then we're going to be able to play that same game we've been playing where we divide both sides by a naught, and then we can bring in the log and do all that again, right? So let's do that. Divide both sides by a naught. We get 1/2 equals e to the, I'm going to write 2.2k instead of k times 2.2. And then this becomes natural log of 1/2 equals 2.2k. I'm not showing that step anymore. I think we've done it enough, yeah? Make sure you type that into your calculator correctly. You should not be getting 0 there. Natural log of 1/2 is about negative, I'm going to write it down here. I'm getting negative 0.69314718. I'm going to go as many decimals as my calculator goes. 2.2k. Then divide by 2.2. So I get negative 0.31507, I'll say, is k. That's my decay rate, right? That's my decay rate. So what is my decay rate written as a percentage? About what? 31.5-ish, right? This is about 31.507% what, decay? This is the rate of decay. 31.5% decay. That's the rate. Okay, so I initially started, I said I don't know anything about this formula other than this, but now I know what k is, right? So let's rewrite the function. So to answer this question, find a function which models this. The function is a of t equals a naught. I still don't know what that is. E to the negative 0.31507t. There it is. That is my exponential decay model for ibuprofen. And now I'm going to ask you some other questions. Let's go ahead and take some ibuprofen now and figure how long it's going to take for a certain amount to decay away, right? So part B. Part B. If you take, let's go with 400 milligrams of ibuprofen, I think I'm spelling ibuprofen right. I think it's right. If you take 400 milligrams of ibuprofen, comma, how much is left 6 hours later? So how many milligrams of the ibuprofen are still actively in your bloodstream helping you feel better, I guess, right? Well, I'm giving you what then? An initial amount, right? And I'm giving you a time. And so if you know the time and the initial amount, you should be able to tell me how much is there at the end. So I'm going to just use that formula. The amount at 6 hours, right? Now, it is important that I put 6 hours here, because if I would have put like how much is in your, how much is still there after 1 day, then you would have to convert the days to hours, right? You have to pay attention to those things. So, but here it's measured in hours, and my original half-life was in hours, so A of 6 is what I took 400 to start, right? E to the negative 0.31507, and then t here is 6, right? Time is 6. So now I'm just going to calculate this, right? No logs necessary. You got something?
Yeah,
60.4 milligrams, right? 60.4 milligrams. I'm going to double check. Not that I don't trust you. I just don't trust you. What?
Can we round to the nearest one?
Yeah, just round. I mean, again, we're not doctors giving dosages or something right now, right? Yeah, 60.4. There we go. Do you all know, can you do 8 here real quick? Can you do 8 in here? 8 hours later instead of 6? What do you get for 8? Should be, I'm going to guess somewhere around 30. 32.16 milligrams. So I don't know if y'all know this, but whenever you are having to do like fever reducing, a lot of times doctors will tell you that you can alternate between ibuprofen and I think it's called acetaminophen, which is like Tylenol. And they say every 4 hours you can do your ibuprofen dosage, and then 4 hours later you do your Tylenol dosage, and then 4 hours later you do your, right? So what's happening there is you're taking your ibuprofen, right? And then you're not taking it again for another 8 hours, right? The ibuprofen. So by the time you get to taking it again, you don't have much of it left in your system, right? Make sense? I mean, there's still some there, but it's decayed down quite a bit. All right, that makes sense? All right, so part C here.
Do all those calculations.
They have apps on their phones that do all of it for them. All right, so part C, I'm going to leave that there. For part C, I want to know how long until you have 1 milligram left. No, let's not even do that. Let's do 0.1 milligrams left in your system. So it's the same situation, right? We took that, what was it, 400 milligrams?
Yeah.
Okay. I want to know how long it's going to take for there to be 0.1 milligrams of ibuprofen in your system, assuming you don't take any more, right? What do you think? Is it going to be a while? Think it's going to be a while?
Yeah.
You think like the next day? We'll see, right? We'll see. So how long means we're solving for t, right? And this is how much we want at the end, right? So I'm going to use this formula. The left-hand side should be what? What I want at the end, 0.1, right? Must equal the amount I started with. What did I start with? 400. This is the same situation, right? Same person taking that 400. E to the negative 0.31507 t, right? And I don't know what t is, and so I have to solve for t. How are we doing on time? All right, what would be your first step here to solve for t? You got to get that 400 out of there before you can bring in a log. So I'm going to divide both sides by 400. It's going to give me an even smaller decimal, right? What is it?
It's 2.5.
Mm,
Give you science notation.
yeah. 0.0025? 3 zeros? 3 zeros, yeah. 3 zeros, 25 equals e to the negative 0.31507 t. Okay, all I did there was divide both sides by 400. Now, log, right? Rewrite this as a log. So it'll be natural log of this, right? 0.00025 must equal that exponent, negative 0.31507 t. Calculator time. $19? Anyone else getting about 19? No?
Got 26.
Oh, I missed a 0. Oops. I missed a 0.
26.
What the hell? Start over. Natural log, 0.12325 divided by negative 0.31507. 26.32. 26.32. So 26.32 is approximately the amount of time. That's in what, hours?
Yeah.
So about a day, right? If you pop 400 milligrams of ibuprofen, a day later, it's essentially gone, right? It's essentially gone. 0.1 milligrams. I mean, it's okay. You all right? All right, let's do some more fun with this. This isn't fun. Okay, that's right. All right, so I'd like, use on your phones, I would like for somebody to look up what the nuclear material was in the Chernobyl nuclear reactor accident. Do y'all know what I'm talking about? Y'all heard of Chernobyl?
Yeah.
Has everyone here heard of Chernobyl? It was in the former Soviet Union, nuclear reactor. Basically, a nuclear reactor creates electricity, right? And it's basically a controlled nuclear bomb. It's not a bomb, but you're using the nuclear reaction, right, of Fusion, fission, what is it?
Fusion.
Fission, we can't do fusion well yet, right? Fission, and you're using that reaction to create heat, and then you create from that steam, and then you drive motors and you create electricity. So these nuclear reactors are controlled, but you can lose control of it. You can lose control of the reaction. And in Chernobyl, this city, the people running the nuclear reactor lost control of it and had this huge nuclear fallout, blow up, and nuclear material got thrown into the air, right? Did you look it up?
Yeah.
Does it say what it is?
Most had it was Caesium-137.
Caesium-137? Can you look up the half-life of it?
It's 30 years.
30 years? Okay. So spell it for me. What is it? Caesium?
Yeah, it's C-A-E-S-I-U-M.
C-A-E-S-I-U-M. Caesium what?
Dash 137.
137. And you're saying that was like the nastiest stuff there, according to them?
I mean,
Yes.
it was the one that had the most.
Okay.
And the longest half-life.
Okay, so Caesium 137, you said it was 30 years?
Yeah.
Okay, 30 years. I'm gonna look this up too because radioactive material Chernobyl. Yeah, okay, we'll go with that. Strontium 90.
Iodine.
Yeah. Okay, we'll go with that.
Okay.
We'll go with that. 30 years. All right. So when did the accident happen? Chernobyl disaster was in, most of you all were not alive.
86.
Was it 86?
Pretty sure.
Let me see, hold on.
Yeah, 1986.
1986. So 1986 is when this happened. All right, it's a huge thing. Nobody lives in this city. Still, today, nobody lives there.
Go visit.
Yeah, you can go visit. You probably won't be there. Well, there's the animals and stuff living there. It's actually, they're doing a lot of research there because they've seen a lot of mutations of animals there and stuff. It's pretty crazy. Anyways, okay, it became real popular a few years ago. HBO had something on it, I think, Chernobyl. Anyway, all right, so the half-life is 30 years. So the amount of material, okay, the amount of bad stuff, okay, so this thing blew up, right? And then what they had to do was they had to get volunteers to basically get on trucks with cement trucks and back up to this hole in the ground and fill it with concrete to try and contain the radioactive material. And these people that did it basically knew it was like a one-way trip, right? Somebody had to do it. So they covered up the core and they encased it in concrete, and then now they've encased it in another like dome around it as well. But from my understanding of it, the amount of bad material in there, like how much got buried, the stuff that's like glowing radioactive material, any guess as to how much it is? How much was there? Any guesses? 10 pounds. 10 pounds. That's less than what you could put in I could put that in my backpack, right? 10 pounds. So let's just say, all right, for the sake of just demonstration here, that in 1986, 10 pounds of Caesium-137, right, was exposed, and here we go, it's glowing hot. So a couple of questions. First of all, what's the exponential decay model for this? Well, let's find that first. So find the exponential decay model. All right, well, I'm going to move a little faster than I did last time. I'm going to use the half-life idea, right? I know that half of the original amount is equal to the original amount e to the k times what? So how long does it take for half of it to go away? 30 years. So my measurement here, everything's going to be in years, right? This is going to allow me to solve for what? What am I going to be able to solve for? Using just the half-life of KCM-137, I'm going to be able to solve for what here? K. And once I have K, I have the decay rate. And once I have a decay rate, then I can tell you anything you want to know. So I divide both sides by A naught. And I get 1/2 is equal to e to the 30k. We've done this many times. Natural log of a half equals 30k. And now I do that on my calculator all at one time, and I'm going to get my decay rate. Negative 0.023105, I'm going pretty far here, is K. So now that I've got that, right? Now that I've got that, I can come up with the actual function, yes? I still don't know the initial amount. Well, I'm going to act like I don't. I know right now that the amount at a certain amount of time will be the original amount, e to the negative 0.023105t. And that's kind of like my master equation, master function, I should say. However, I just told you that, and again, this is from some research I did years ago. I could be wrong here. I remember reading that there's only about 10 pounds of really bad stuff in that core. So let's just say the initial amount was 10 pounds, all right? So we're measuring things in pounds. So the amount after a certain amount of time should be 10, that's the 10 pounds, e to the negative 0.023105t. There we go. Now we have a new formula because the original amount was 10. This is pounds, LBS, pounds, right? And our time here is measured in what? Years? Okay. So anyone want to guess what my next question is going to be to you?
What was it after? Oh, what is it?
What is it today? How much of that KCM-137 is still brewing in there right now, 2023? So part B, how much is there now? 2023. But you know what, 2024. Nah, it's not 2024. We'll go 2023. So what am I asking you to do then?